Yeah, hey, I'm Niels. I'm the senior rendering engineer for Crytek, and I'm here to share a bit of the experience, what happens when you drop Robinson on a mobile phone. Robinson is actually a VR game that is about a little boy stranding on a planet, and we published that in 2016 for PSVR. And then later for HTC Vive and Oculus Rift. So that are actually very different platforms. The PS4 is the UMA architecture, just like a mobile phone. And the other ones are PC. We had NUMA versus UMA differences built into the engine. So when we tackled Vulkan on the mobile phone, we didn't have to change very much to get optimal streaming and stuff like that, because memory management is very important and you don't want to copy stuff around which you already have in your mobile device. For us, it was basically a learning experience. We had the hope to support GVR with Vulkan, which wasn't the case back then at GDC 2017. And still today, Vulkan has well, no connection to any VR interface in the moment. The Android system part of the CRYENGINE we didn't need to touch, because in 2015 for GDC we made an equally quick and dirty hack for Crysis 3 MP multiplayer on a Tegra device. That Tegra device was much more powerful than an Android mobile device, and it ran on OpenGL. So basically that was an exercise in orientation and evaluating how is the performance of the GPU, what are the tools that we have, and how we can improve on that. And I brought the demo here. So this is an S7 Edge. I think it runs at 1920 by 1080. This is our loading screen. And this is a sequence from the beginning of the game. It's obviously not VR, because we don't want to. We don't have the capability to write everything which is in the regular Oculus driver with asynchronous submissions and hair tracking and all of this, which we would have to make ourselves, which obviously is possible. By default, it's on Rails, and you can't hear it, sadly, but actually Higgs, which is this little AI in the ball with the eye, is talking to us, and there are sounds in the background. And for fun, we also made it, this is very difficult to see, made it react to the orientation of the cell phone. It's kind of sad, but I mean, you can come forward after the talk and then you can try it yourself. It's not a big deal. As you saw, it runs about at 45 frames per second, sometimes a bit better, sometimes a bit worse. We also experimented with a Nexus 6P, which was, I would say, a failure in the Samsung S7. This is a version with an Exynos and a Mali T880. The Nexus 6P has an Adreno chip, which has severe limitations, so it didn't work out very well. Okay, so regarding Vulkan, we reworked the entire CRYENGINE over the last years to be more abstract. Initially, it was entirely DX11 model, so even the OpenGL renderer that we used on the Tegra device was actually DX11 to OpenGL translation. So this time we made everything abstract, and all the APIs that we are supporting, like 11 and 12 and Vulkan and so on, is natively integrated and has all the optimizations, PS4, Xbox, and so on. So this was not our first attempt at Vulkan. Our PC version ran relatively stable at that time, but it was our first attempt when running Vulkan on a mobile device. Our Android bridge is SDL, open source project, and there was no Vulkan support at that time. So I ripped out the entire default OpenGL context initialization, which happens by default, and used our regular VK surface and VK swap chain functionality that we had to create the necessary objects, Vulkan objects, to run on an Android window. When we ran it, just like that, a lot of bad things happened. And no validation errors were generated. There, in the introspection, when we tried to find out what happened on the Adreno chip, it only supported 4 descriptor tables per stage and stuff like that without any validation error when you turn on the validation layer. Besides that, there were tons of formats which were not supported. I mean, Robinson ran on the regular PC GPUs, which all support block compression. So we had to find corresponding mappings to EAC. Luckily, the asset workflow was already in place because our OpenGL implementation had all the EAC codings enabled. Then there were some surprising fails. There were specific S-norm targets which weren't available. We mapped them to half-load formats. There were some, I think that both, I'm not sure which of them didn't support 32-bit float depth stencil. Then we had to go back to D16. There was also a problem getting something as basic as a RAD16, which is an integer format, single channel integer format, which would actually alias the D16. So we had problems actually accessing this D16 by aliasing the views. We didn't pick ASTC over EAC because, well, we just worked 1 month on it. And it was just an experiment, so it's not that, that we have to make the whole feature list complete. So basically we ran through the code and made a large part of the code base flexible. There was the situation where the requested swap chain mode of FIFO wasn't available and we had to get back to mailbox. There was the situation that you ask for triple buffering, so that you get 3 back buffers and you actually got 4. There was the problem with the specific texture formats and like, for example, the Mali T880 on this S7 does not have anisotropic filtering. On the Adreno, we don't have any cube arrays or 3D samplers, and where the geometry shader and tessellation support is all over the place. Most of them basically don't support any of that, and there's a problem. So if you're from a PC environment, you know that you always can bind 8 render targets and you basically have unlimited descriptors and or you have 256 HLSL shader slots, and all of this is, the numbers are not very large. Most of the time it's 4 render targets. Sometimes you have, because of a bug, just run descriptor table. Sometimes you have 4 descriptor tables. So you have to well, keep the engine running under all of these restrictions and just not quit and say, oh, sorry, you can't run. That is not necessarily a problem to allow the system to downcast the swap chain modes. That's not a big deal if you're using FIFO or Mailbox or something like that. You can write your code so that the texture formats can downcast to compatible formats that are available. It's just you have to make a lot of reflection and on the device and see what you can do. In the case if you really need a 3D texture, it becomes a bit complicated, but I mean, having alternatives available, algorithmic alternatives is always a good thing, I think. Our shaders are a lot. We have 45,000 lines of HLSL code. When we supported the OpenGL, we had a transcoder that translated HLSL to GLSL, which was HLSL-CC, which is also used in Unity. We heavily modified it. We added compute shader support and all kinds of different sampler type supports and so on. So that thing became feature complete in the end, basically. The problem is that under Vulkan GLSL is not GLSL. Under Vulkan GLSL is a Vulkan-specific GLSL with different annotations and different syntaxes, and so I had to go over HLSL-CC again and make a lot of adjustments, like how to pass metadata from HLSL to SPIR-V, because you want to reflect on the SPIR-V. Basically, well, this is an exercise in masochism, I would say. So luckily, excuse me, luckily this is over, because now we have, I think it's called DXC or DBC. We have a native HLSL to SPIR-V translator, which has been developed by Kronos together with a few folks of Google. So this is not anymore, but we don't want to repeat that. So we ran in a lot of early adopter issues, even after we thought we make everything right and we adapt to all the different parameters of these devices. Like we said, on the PC it ran, there were no validation errors. On the devices, there were no validation errors, but sometimes it was completely broken or it looked slightly different. Specific parts of it looked different, flickered, or some constant buffer values weren't transferred to the draw in a correct way or something like that. We don't know really what happened there. So on the Andreno, like I said, there was absolute no QMap array support, so we limit that to 1 cube map. There were problems with the constant buffers, so we actually made big arrays in the shaders where we hard-coded the lights, like for example for this demo. This is not because of performance reasons. This is really because the device just didn't, or the driver just didn't do what we told him to do. Yeah, and then there was a problem on Andreno, which was relatively severe. We couldn't actually toggle descriptor tables, so we bound one monstrous descriptor table and we dynamically offsetted it with every draw call. which is a solution on several, basically all of it is solutions just to make the demo running. I cannot recommend that you try something like that for delivering a game. So after it ran with the expected result, the next problem was performance. Well, this is Robinson, which means that our baseline performance is a PS4. The subsequent releases on Steam and on the Oculus Store were for PCs, which means open-ended. You can run it on a Titan, so there were no problems. This is a comparison between an S7 and a PS4, which is in some ways very severe. Here the CPU is a Exynos MP12, which is a 2.3 gigahertz 4-core. It runs in Big Little, I think. So in theory, we could have 8, but we could only use 4. These gigaflops are without Neon. Neon is a vectorization instruction for ARM, which, if you would use it, would quadruple the gigaflops, which means you would be at 9.2 versus 102.4 gigaflops. In this demo, it's not such a big problem because we don't have any collision detection, we don't have any complex CPU code. But if you would actually try to calculate any of that, then some problems would occur. The GPU is in a similar ballpark. The Mali T880 has 260 gigaflops versus 1.8 teraflops of the PS4. Basically, that these gigaflops don't necessarily mean that much. You also have fill rate limitations. You have vertex throughput limitations and so on. So this is just like a rough idea about what this. The biggest problem, actually, even if it doesn't really look like that, is the memory bandwidth. On the PS4, we have GDDR5 shared between CPU and GPU, and on the S7, we have LDP DDR4, which is low power DDR4, which is actually double rate, so it's 28.7 gigabyte per second versus 176 gigabyte per second. And this, because we're implementing deferred shading, we have a lot of post-processing effects, which are full screen effects. Our cost is basically the cost of everything after the GBuffer is proportional to the resolution, and the bandwidth cost is proportional to the resolution as well. So you can run a very small resolution and run the whole pipeline, or you have to make cuts. And then there are the thermal issues, which we completely ignored, but this device behaves very nice. The Tegra that we ran 3 years ago was running hot after 5 minutes and was throttling, which didn't happen with this, which is pretty nice. So the rendering framework of Robinson is a full tile deferred shading pipeline. We're running a GBuffer pass, which means all the draws are writing out material attributes into different render targets, and we are storing depth, and then afterwards we can do all kinds of magic things with it, like AO, screen space AO, or the lighting or depth of field, motion blur, all of these things can be done on this GBuffer. Here we have three bound render targets. Each one is 4-channel 8-bit, which means we have about 24 bytes in 3 render targets, and it's relative fill rate heavy. It uses a lot of the capacities of the ROPs. And if you look at the pure memory bandwidth occupation, just looking at it, that's about almost a gigabyte per second. You can just look 28 times at such a buffer on a mobile device, and then you eat up all your bandwidth. So that is pretty problematic. That is just one 2560 by 1440. So we had to find an alternative. In the beginning, we experimented with 4-bit render targets. These are 8-bit render targets, so that would then go to 12 byte, but we still would be ROP limited because we still have 3 render targets bound. So our idea was we reduce the entire 3 render target GBuffer to a single 4-component render target. In a previous version of Crysis, excuse me, we already employed a technique that we are storing some information just on even and alternating information on odd pixels, which results in a half-size rendering, and not a quarter-size rendering, but a half-size rendering. Here we store albedo at full resolution. So the basic non-metallic surface color is full resolution. And then we are storing normal smoothness and reflectance at alternating positions, like you see in the little square there. The reflectance is non-color. We could get away with it in this demo, but normally you would actually want to have colored reflectance, which needs more time. So we just wanted to see how fast could we get CryEngine running without major modifications. Can we actually get into the direction of VR performance? So here we have examples of this tiny micro GBuffer. So there are the 3 render targets. The upper one is the RGB part, and the lower one is the A part. So these are really just 3 render targets. And everything, all these 6 things are in those 2. If you zoom a bit nearer, you see the cost. The cost is that, of course, you're undersampling your edges. You sometimes see that every even odd line just forms a diagonal, except instead of like the regular diagonal that you have in the full resolution GBuffer. The meaning of the alternating pixels here is also not always the same, so it's a bit difficult to label this. It's just that you get the idea what's the price. We actually have an edge-aware reconstruction of this in the lighting path, so it comes out in acceptable quality. In other areas, like we render HDR, and we tone map the HDR later. Other bandwidth savings we reach by reducing the precision of the HDR buffer from regular halves to 11-bit halves, even lower precision floating point representations. We kicked stencil out so that we could use D16 instead of D24S8. And Robinson as a VR game already forfights a lot of the effects. We don't have depth of field, we don't have motion blur, because all of this stuff just in the VR environment breaks the illusion that you are really in the scene. It breaks immersiveness. So we had to turn off a lot of the additional nice making post-processing effects like the subsurface scattering, because it requires space in the GBuffer. We also don't have any screen space reflection because it eats way too much bandwidth. It's basically ray tracing rays in screen space, which probably eats up the entire bandwidth that we have there. No volumetric fog. And that's the 3D texture. Back then, we wouldn't have had an alternative like two-dimensional fog or something like that. And of all the, like I said, of all the other post-processing effects, we only needed tone mapping and the vignette effect, so that you have the simulation of a reduced field of view. And we made one Uber shader out of it, which looking at the bandwidth is, I think, the correct suggestion that you merge all your post-processing or all your screen space passes, if possible, into one big shader, because the ALU capacity of the mobile GPU is way above the bandwidth. So instead of read, write, it's better to just read once and then drop 5,000 instruction shader and then only write once. All right, so our conclusion of the project regarding games on Android, the effort to make Vulkan run on the mobile platform from our PC platform was relative minor. We were 4 people working 1 month on it, so you could basically say one of us worked 1 month on polishing all the problematic cases of Vulkan on mobile. The biggest problem is the variety of targetable hardware. Like we had in the talks before, you can make a business decision like it's not viable to target this and that much hardware, but as a software engineer you also have the problem there's tons of hardware which is almost equivalent and there's just one checkbox missing, or here's just one checkbox missing. So you have to write your engine relatively flexible that you can adapt yourself to it. We also didn't really believe that, like, if we would render this in stereo, then we would be at 20 FPS maybe, which is way below what is supportable by a person in a VR device. But we didn't really expect that to happen. But basically, if we have a GPU that is twice as powerful as a T880 from Mali, then we actually might get into the direction of having something like this in VR on a mobile device. We were very happy that in principle it was possible to run a fully physically based shading pipeline on a mobile device with actual tiled deferred rendering and forward plus. And while I didn't observe any compute queue in Vulkan on any of these tested devices, I'm pretty sure that the modern mobile devices are coming up with a compute queue earlier than later. Vulkan is very well positioned because the CPU overhead is very low. You have a lot possibility to control your GPU performance. You can submit stuff in different ways. That's contrary to OpenGL, which is a very large black box. It's difficult to optimize for it because, I mean, the driver can make something and then you don't know about it, and then everything you did was in vain. While for Vulkan everything is relatively well defined. The conclusion for Vulkan on Android. Well, I already announced a few of those. The good part is that in Vulkan you can do multi-threaded rendering. Our entire renderer is actually submitting the big scene graphs in a multi-threaded way. This is very, very difficult in OpenGL. You can open concurrent contexts, but I wouldn't suggest it. It's probably not worth it. What's very nice is actually the renderer subpasses of Vulkan, which requires a huge refactoring of your engine. It basically means that little tiles of your shader run once through the whole process. So let's say you have 10 passes, so then this tile is run 10 times, and then another tile is run 10 times, and so on. So you're having the possibility in the driver to actually merge parts of that using optimal memory I/O and stuff like that. But that requires making dedicated changes in the architecture. So, well, at the end, I want to thank everyone who participated, Alex, well, myself, Theo, Mathis, Nico, and the other Nico. And without the guys working on these tools, almost nothing of this would have been possible. HLSL is an open source project which we could manipulate, give back. SPIVI Cross is, I think, from Kronos now. SDL2, standard stuff since years, and well, we have probably used a few more open source tool chains to make all this weird stuff happen where we don't have any official support. And special thanks to Li Zhang and Ehsan Naziri, who are actually from Google, I think. They are working on the DXC, which is this new SPIVI backend, which removes all the problematic things with shaders. And well, Crytek is hiring, so if you want to work on mobile for the CryEngine, write us an email. Well, questions?
A question about timing that you briefly mentioned. Mm-hmm. Because it looks to me that some of your bandwidth problems could be alleviated by not spilling the tile after every pass. Mm-hmm. And you mentioned that that would require a re-architecturing of the engine. Is that a problem of resources, in a sense that it would take you a long time to re-architect the engine, or is the problem of the API that is not making your life easier?
No, the problem is that the last missing piece in the CryEngine is that we don't have a render graph. The big API makers are evangelizing the idea that you submit the whole framework as a render graph. And if you generate the render graph dynamically every frame, like you don't write the render graph in code in your CPP and it's static. If you have a manager that generates a render graph every frame to schedule all of this, then you can actually generate the render subpasses for Vulkan automatically. Because you have to specify, okay, this is an input. Which state is this input? Is this cleared? Do I read from it? Is it read modify write? And so on. So you have to annotate a lot of the structs that you use generating subpasses on Vulkan, and it's not recommendable to make this manually. So you have to have an automated system to generate render graphs in data, in memory, and then it's a trivial thing.
So it's a high-level issue?
Yes, it's a high-level issue, yeah.
You can potentially lay down the GBuffer, do the lightning pass in a tile, and then move on to the next tile.
Yeah, that's even independent. In Vulkan, you have the possibility, like what we saw in these capture tools, you had the render targets where you write to, and you have the depth stencil. And if you express something as subpasses in Vulkan, you're basically describing a chain of shaders, how they interact with each other, how they are feeding data from one shader pass to a next shader pass. It's similar to how we describe in the shader stages between vertex shader and pixel shader and how they're interacting with each other in a data transportation way. So on Vulkan, you have one step above that so that you're basically putting entire draws into relation to subsequent draws. And that brings a lot of performance. Can potentially bring a lot of performance, like we have the imagination ships, which are actually ships which have hardware support for this mechanism. So it doesn't spill to memory. We have this problem that the LPDDR4 is very slow. So the imagination ship has an on-chip buffer where he spills the data between the different subpasses, not into main memory. He spills it into a special dedicated piece of hardware. And you can maybe get away with 10 times speed up by that. So the bandwidth of this internal area of the chip is just 10 times faster than LPDDR4.
You mentioned texture formats. Did you guys use ETC2, or did you find that not sufficient, or, I mean, instead of ASTC?
No, for us it's not sufficient. We are almost using every texture format under the sun.
So I believe that's the only one across all Android.
Yeah, no, there are weird permutations of ETC2, which provide 1 channel, 2 channel, and additional bit depths until 11-bit. And we are using all of those too, yeah.
And are you going to continue with your experimentation, or are you going to wait for mobile to get a little bit better?
Maybe it depends on how fast OpenXR is going to finalize. There's an initiative from Kronos called OpenXR, which encapsulates OpenAR, OpenMR, and OpenVR, where they want to attach Vulkan to, and then we have a real VR interface, and then we definitely back experimenting. I mean, the problem for us is the gap between the PS4, which is our regular min spec, and the next mobile device.
It's great to see you working on with our open source teams on the shader compiler stuff. Have, on the validation errors you were seeing with the device physical limits, have you submitted an issue to the open source GitHub project for the Vulkan validation layers? There's a GitHub project for Vulkan validation layers.
All right.
And you were saying there was, they were not catching issues with physical limits?
Yes.
Have you submitted a bug to that GitHub project?
No, because the state of the Andreno driver was so shaky that we didn't expect any. Well, okay, I understand that the validation layer is a different part from the driver, but for us, it's not transparent if we fault the validation layer or if we fault the driver. But this is 1 year ago, right? Even on the PC, the validation layer was not firing for some stuff which was obvious.
Okay.
Then half a year ago, there was a moment where the validation layer fired too much. And now we have a moment where the validation layer is probably in a good place.
Okay, good. Thanks.
Regarding the PC validation layer problems, I think we submitted bug reports. Yeah.
It should be unified, so whatever you're seeing on PC should work on Android as well.
Okay.